From the dawn of humanity, we have gazed up at the stars, our eyes filled with wonder and our hearts brimming with questions. The night sky, with its twinkling stars and mysterious galaxies, has always been a source of inspiration and curiosity. We have pondered our place in the universe, seeking to understand the vast expanse that stretches beyond our sight. The Milky Way, our galactic home, is just one of billions of galaxies, each containing countless stars and potentially habitable planets. This innate curiosity has driven us to explore the unknown, pushing the boundaries of knowledge and technology. From the early days of rudimentary telescopes to the sophisticated space probes of today, our quest for understanding has never ceased. Today we stand at the cusp of a new era in space exploration, one marked by groundbreaking advancements and profound implications for the future of humanity. The launch of rockets, the deployment of satellites, and the construction of space stations are just the beginning. Recent years have witnessed a surge in space exploration activities fueled by both public and private initiatives. Companies like SpaceX and Blue Origin, alongside agencies like NASA, are leading the charge into this new frontier. We have seen the rise of reusable rockets, a revolutionary development that significantly reduces the cost of space travel. These rockets, capable of landing back on Earth and being launched again, are paving the way for more frequent and affordable missions. The development of advanced propulsion systems such as ion thrusters and nuclear propulsion promises to shorten travel times and expand our reach within the solar system. These technologies are crucial for future missions to Mars and beyond. The increasing use of artificial intelligence in space missions is another game changer. AI-controlled rovers and robotic arms are performing tasks that were once thought impossible, from navigating the Martian terrain to assembling spacecraft in orbit. These innovations are not only transforming our understanding of the cosmos, but also making space travel more accessible and affordable than ever before. The International Space Station, a symbol of international cooperation, continues to be a hub for scientific research and technological development. As we delve deeper into the universe, we are confronted with fundamental questions about our place in the cosmos. Are we alone? What is the nature of dark matter and dark energy? How did the universe begin, and what is its ultimate fate? The discovery of thousands of exoplanets orbiting stars far beyond our solar system has opened up new possibilities. Some of these distant worlds lie within the habitable zone of their stars, where conditions might be right for life to exist. Some of these exoplanets may harbor life, challenging our assumptions about the uniqueness of life on Earth. The search for these potentially habitable worlds is a driving force behind many current and future space missions. Scientists are examining data from telescopes and space probes, looking for signs of life and trying to understand the conditions that might support it. This research is not just about finding new planets, but also about understanding the potential for life in the universe. The search for extraterrestrial life is no longer a topic confined to science fiction, but a serious scientific endeavor with the potential to revolutionize our understanding of biology, evolution, and the very nature of existence. As we continue to explore, we may one day find that we are not alone in the cosmos, and that discovery will change everything. For decades, the high cost of space travel posed a significant barrier to exploration and innovation. Launching a single rocket into space required enormous resources, limiting the frequency of missions and the scope of scientific endeavors. However, the advent of reusable rocket technology has fundamentally changed the economics of spaceflight. Companies like SpaceX and Blue Origin have pioneered the development of reusable rockets, capable of launching payloads into orbit and returning to Earth for refurbishment and reuse. This breakthrough has dramatically reduced the cost of launching cargo and humans into space, opening up new possibilities for scientific research, commercial ventures, and human exploration. The implications of reusable rockets extend far beyond mere cost savings. By increasing the frequency of launches, we can accelerate the pace of scientific discovery and technological development. With more frequent access to space, researchers can conduct experiments, deploy telescopes, and gather data at an unprecedented rate. This will undoubtedly lead to new insights into the workings of the universe and our place within it. While reusable rockets have revolutionized access to low Earth orbit, they represent just the beginning of our journey into the cosmos. These technological marvels have made it more cost-effective and efficient to send payloads and even humans into space, but they are primarily designed for relatively short trips within the vicinity of our planet. Reaching farther destinations in our solar system and beyond requires even more advanced propulsion systems. The vast distances involved in interplanetary and interstellar travel present significant challenges that current technology is only beginning to address. The journey to Mars, for instance, takes several months with our current propulsion methods, and traveling to the outer planets or beyond our solar system would take years, if not decades. Chemical rockets, while powerful, are limited by their fuel efficiency and thrust-to-weight ratio. These rockets rely on the combustion of propellants to generate thrust, which means they need to carry large amounts of fuel, making them heavy and less efficient for long-duration missions. The limitations of chemical propulsion become more apparent the farther we aim to travel. To overcome these limitations, scientists and engineers are exploring alternative propulsion methods that could enable us to travel faster and farther than ever before. These innovative approaches are not just theoretical. They are being actively researched and tested in laboratories and space missions around the world. The goal is to develop propulsion systems that can sustain long-duration missions, reduce travel time, and increase the payload capacity of spacecraft. One promising avenue of research is ion propulsion, which uses electricity to accelerate ions, creating thrust. This method is already being used in some spacecraft and has shown great potential for future missions. Ion propulsion systems work by ionizing a propellant, such as xenon, and then using electric fields to accelerate the ions to high speeds, producing thrust. Ion thrusters are highly fuel efficient, requiring far less propellant than traditional chemical rockets to produce the same amount of thrust. This efficiency makes them ideal for missions that require long periods of continuous thrust, such as traveling to distant planets or maintaining a stable orbit around a celestial body. The reduced fuel requirements also mean that spacecraft can carry more scientific instruments or other payloads, enhancing the mission's overall capabilities. This makes them ideal for long-duration missions to distant planets and moons. For example, missions to the outer planets such as Jupiter and Saturn, or even to the Kuiper Belt and beyond, could benefit greatly from the extended thrust and fuel efficiency provided by ion propulsion systems. NASA's Dawn spacecraft, for example, used ion propulsion to travel to the asteroid Vesta and the dwarf planet Ceres. This mission demonstrated the practical application of ion propulsion in deep space exploration, showcasing its ability to perform complex maneuvers and travel vast distances with minimal fuel consumption. Another intriguing possibility is nuclear propulsion, which harnesses the immense energy released by nuclear reactions to generate thrust. Nuclear propulsion systems have the potential to revolutionize space travel by providing much higher energy densities compared to chemical propellants, allowing for faster travel times and greater payload capacities. Nuclear thermal propulsion, for instance, involves heating a propellant, such as hydrogen, to extremely high temperatures using a nuclear reactor, expelling it through a nozzle to create thrust. This method can produce significantly higher thrust levels than chemical rockets, making it a promising option for crewed missions to Mars and other distant destinations. Nuclear propulsion systems offer the potential for significantly higher thrust-to-weight ratios and shorter travel times compared to chemical rockets, making them well suited for human missions to Mars and beyond. The ability to reduce travel time is particularly important for crewed missions, as it can help minimize the health risks associated with prolonged exposure to space radiation and microgravity. As we continue to push the boundaries of space exploration, advanced propulsion systems like ion and nuclear propulsion will play a crucial role in enabling humanity to reach for the stars. The vast distances and harsh environments of space present significant challenges for human exploration. The sheer scale of the cosmos, with its countless stars, planets and galaxies, is both awe-inspiring and daunting. Human beings, with our current technology, are limited in how far we can travel and what we can endure in space. The vacuum of space, extreme temperatures and high levels of radiation make it a hostile environment for human life. To overcome these challenges, we are increasingly relying on artificial intelligence, or AI, and robotics to extend our reach and enhance our capabilities in space. These advanced technologies act as our eyes and ears in the cosmos, allowing us to explore and understand regions of space that would otherwise be inaccessible. Robots can withstand harsh conditions and perform tasks that are too dangerous or impossible for humans. AI-powered systems can analyze vast amounts of data, operate autonomously, and adapt to unforeseen circumstances, making them invaluable assets for space exploration. These systems can process information at speeds and volumes far beyond human capabilities, enabling us to make sense of the immense data generated by our space missions. They can also learn from their experiences, improving their performance over time. One key application of AI in space is in autonomous navigation and spacecraft operations. Navigating through the vast expanse of space requires precise calculations and constant adjustments. AI systems can handle these tasks with remarkable accuracy, ensuring that spacecraft stay on course and reach their destinations safely. AI algorithms can process data from sensors, star trackers, and other instruments to determine a spacecraft's position, orientation, and trajectory with remarkable precision. These algorithms can quickly analyze the data and make real-time decisions, allowing the spacecraft to respond to changing conditions and avoid potential hazards. This enables spacecraft to navigate autonomously through the solar system, making real-time adjustments to their course without human intervention. This autonomy is crucial for missions that travel far from Earth, where communication delays make real-time control from the ground impractical. AI is also playing a crucial role in data analysis and scientific discovery. The vast amounts of data collected by space telescopes, probes, and other instruments can be overwhelming for human analysts. AI systems can help manage this data, identifying important patterns and insights that might otherwise be missed. Space telescopes and probes generate massive amounts of data, far exceeding the capacity of human analysts to process. This data includes images, measurements, and other information that can provide valuable insights into the nature of the universe. AI algorithms can sift through this data, identifying patterns, anomalies, and potential discoveries that might otherwise go unnoticed. These algorithms can detect subtle variations and trends that are difficult for humans to see, leading to new discoveries and a deeper understanding of the cosmos. This is particularly important in the search for exoplanets, where AI is being used to analyze subtle variations in starlight to detect the presence of orbiting planets. By examining the light from distant stars, AI can identify the tiny dips in brightness that occur when a planet passes in front of its star, revealing the presence of worlds beyond our solar system. This capability is opening up new possibilities for finding potentially habitable planets and understanding the diversity of planetary systems in the universe.